Hello everyone and welcome to today's lecture. As you might know, we are going today to discuss about memory management. And here you can see the outline of this presentation. We will cover some basic aspects of memory management. We will initially talk about the memory organization fundamentals so that we clearly understand the difference between virtual and physical memory. Followingly, we'll see how the operating system manages the available memory and how it is exposed to the eyes of the programmer. And lastly, we'll cover some topics closely related to the memory allocation, its problems, as well as the different possible techniques that can be applied to counter these challenges. Now, to begin with, let's clear things up about physical and virtual memory first. Physical memory refers to the actual memory device, either it's DRAM or whatever. It is of a certain size and each of its bytes can be accessed through load and store instructions by providing the correct physical address. However, the size limitation of the physical memory was a big constraint for the programmers, and therefore the concept of virtual memory was introduced. It's nothing more than a memory management technique that provides to the programmer the notion that the amount of memory space that he has and he's eligible to use is huge in size, and it can be used by his application. Its mechanisms are managed by the operating system itself, and with this abstraction, an extra level of address translation is introduced, which is required so that from the virtual memory address, we can associate each virtual memory address with its own physical memory address, and thus we can access the device, the underlying device, correctly. Yeah. So having mentioned all that, let's move on to see how this translation is performed in practice. There are two most common approaches related to this subject. The first one is called paging and the second one is called segmentation. To begin with, the virtual address space of a process is split and mapped into physical memory pages. The typical size of a page is 4 kilobytes. However, nowadays we have even larger pages, so-called huge pages, which can be in terms of megabytes or even gigabytes. Now, what happens when the process requests to access a specific address of this virtual address space? This address is comprised by the virtual page number and the page offset, which indicates where the data is stored within the page. The first thing that is done is a lookup in the translation look-aside buffer, or TLB for short, which is a cache storing address translations. It is a part of the chip's memory management unit, or the MEMU, and the TLB stores the recent translations of virtual memory to physical memory addresses and can be called an address translation cache, essentially. If the requested address is located in TLB, we have a so-called TLB hit, and we can proceed as the translation to the physical address is successful. However, if it's not the case, a lookup in the multi-level page table has to be done. A page table is the data structure used by a virtual memory system inside the operating system, where it stores the mapping between virtual addresses and physical addresses. The lookup is performed with some bitwise logic based on the virtual page numbers. Let's assume for now that translation is found in the page table, and since we have a page table hit, the TLB is updated with a correct translation and the operation is repeated, which means that at the second time that the operation is done, we have a TLB hit which leads us to the correct virtual to physical address translation in the end. Note that this operation is quite costly, and therefore we try to avoid this as much as possible when we have applications. In the unfortunate case that the address translation cannot be found though in the page table, then we have to deal with a page fault and resort back to the disk in order to find the appropriate page. The respective exception handling software that handles the page fault is invoked. In this case, if we have spare space, as here in the yellow, in the physical memory, we simply fetch the correct page from the disk. However, if there is no space, then a page should be replaced. Based of course on the implemented replacement policy, a page is chosen, here for example the red, and if it's marked as dirty, which means that it was modified during its lifetime inside the physical memory, the page is written back to the disk and is replaced with our requested page in the end. This operation is called swap, and after this comes to an end, the page table and the TLB are updated accordingly, and the operation that caused the page fault is re-executed, hitting the TLB and being able to do the actual virtual to physical memory address translation. Now, the segmentation approach is based on the fact that the virtual address space is split into segments with variable length. Each segment represents a different part of the program. These segments are loaded into memory during the execution time of the application. The translation here is also similar with the paging approach. The main difference is that instead of having a multi-level page table, there is a segment table, as the one you can see here in the slides, which correlates the segments with their respective physical memory addresses. The main advantage of this approach is that it has no internal fragmentation, which we'll see in a bit later, and that the segment table consumes considerably less space compared to the multi-level page table that is used in the paging approach. As a next step, let's see how the application memory is actually organized. It is split in 4 different segments, these colored boxes here on the slide. The first one contains the actual code of the program, of the application. The next one is where the static and global variables are placed. Then we have the stack. The stack is a contiguous memory region, and the allocation process in this region is being taken care by the compiler itself. Whenever a function is called, for example, the appropriate local variables are allocated in the stack, and when the work is over, the occupied space gets reclaimed. It's important to mention that the size of the stack is fixed during runtime. Probably you have heard of this famous stack overflow. The fourth part of the application memory is a heap. Heap memory can be allocated in any random order, and the size of the heap is not predefined and can grow during the application's runtime. In this region, the memory management is a purely programmer responsibility, which means that programmer has complete control over what is allocated there and how these resources are managed. Memory allocation, the allocation should be explicitly instrumented in the program code, and improper handle of this region can lead to quite severe problems such as memory leaks or fragmentation. Here, let's see how actual memory allocation is being performed by the programmer. Here you can see the heap memory allocation exposed interface. I'm sure most of you have already used, if not most of these calls that you can see here. But let's start with the fundamentals. sbrk, as it's also mentioned in the slide, is one of the basic memory management system calls. What it does is extending the available heap memory by the requested size, of course, if it's possible and the resources are available. Malloc is the main function for memory allocation. It reserves a memory block by at least the requested size and returns a pointer to this allocated space. Realloc, as its name suggests, reallocates memory objects. It can either enlarge or shrink in size. Realloc returns a pointer to the new allocation of the object in the heap while freeing the previous one that is resized. Free is a quite important, often neglected function, I would say, as it releases the memory that an object occupies, making its space reusable from the application. mmap is a function that allows files or devices to be directly accessible to the program in its virtual memory address space. It enforces demand paging, which means that at the time that the mmap is set, the actual file content is not backed by the physical memory, but the content is actually read from the disk of the device when a specific location of this mapped region is accessed for the first time. It is worth mentioning that one major reason to choose memory mapped file I/O is performance. Now that the semantics are clear, let's dive in and see how the block selection can be done under different selection policies when you perform allocation. Let's start with the first fit approach first. When a request for a memory allocation is triggered under this policy, the first block that is found with a precondition that is large enough to serve the request is chosen, and the requested block is allocated inside this specific slot. As we can see here in the example, this green box is where the allocated block will be placed, and in this allocation request, the search starts from the starting address of the heap and goes further until the appropriate free block that can accommodate our request is found. Then we have the next fit policy. In this policy, the first block that is found during the search process and can accommodate the requested memory size is reserved for each specific allocation. So here you can see the request block 1 gets allocated in the very first block that is found. But the difference with the previous approach is that the search starts from the ending address of the previous allocated block. So here, when you have the second requested block, the first block that will be checked will be the one directly above the other one, and there we can have our allocation. Lastly, we have the best fit, and under this policy, when an allocation is requested, all the heap blocks are examined so that the best one is chosen. Let's see how it's done in a simple example. Here we have this requested block, and actually what we do is we check every green block here that is free and identify which one is the best place to go. Now we have a smaller block here, which we know that it fits between the allocated block 1 and the unallocated region above. What this algorithm will do is we check every possible block, but eventually we'll identify that this exact block is the one where it should be placed. Now, one major problem that memory management software has to take care of is the fragmentation, as we mentioned also earlier. As someone could have observed in the previous examples, consecutive allocations and frees can incur having way too many variably sized but fixed blocks. And let's see what happens by example. So when we free this allocated block 1, we see that we have 3 different blocks there, which can be comprise the whole a larger size, but still split. So this is called external fragmentation. The solution to this issue is coalescing, which is a technique for merging adjacent 3 blocks so that the wasted memory is minimized. Here, for example, without this approach, we see that this requested block cannot be allocated in any of these three different blocks because it doesn't fit. However, if we manage to merge them, then we would have enough space for this requested block to fit in, right? Now, external fragmentation is not the only issue. When a block request comes, quite frequently a larger block is chosen, which means that a part of this block, for example, as you can see here, a part of this block remains unusable. And this example showcases exactly this behavior. This phenomenon is called internal fragmentation, and the level to which it occurs depends, of course, on the chosen allocation strategy as well as the granularity of blocks and the allowed padding for each allocation. Now, as we said, we have different possible block selection policies. We will also go quickly over more proper allocation strategies, and here you can see a list of them, of the most commonly used, I would say. What we mostly care about when making an allocator is which blocks are usable and which are not. Therefore, the representation and the block segmentation plays an important role. The first approach, is the free bitmap representation, where, as the name indicates, its block state is represented by a single bit in a bitmap. The second one is a linked list implementation, which maintains a list of the free memory blocks available in the heap. Another good technique is the segregated fits, and in this one, a group of free lists is maintained, each one of those referring to different sized block chains or lists. Lastly, we have the body allocation system. When having this strategy, each memory block, starting from the whole available heap, can be split into 2 sub-blocks, which we call bodies, and that's how it takes names, which each one of those is a power of 2 in size. This process can proceed further, creating a hierarchy of bodies with differing sizes. Each technique has its pros and cons for that reason, and many programmers also tend to use custom hybrid allocators to better serve their unique purposes and match their applications allocation patterns. Now, having seen all this, let's summarize what we figured out in the previous slides. First, we saw what's the difference between the physical and the virtual memory. So the OS provides the virtual memory abstraction that requires translation to the physical memory in order to access the actual data from the application's perspective. Then we saw what is the difference between stack against a heap. So the stack is a contiguous block of memory managed by the compiler and has a fixed size, and while the heap is dynamically managed and can grow over the application's lifetime. And lastly, we saw the selection policies, which are implemented when allocating memory with different algorithms and with different pros and cons. And finally, the allocation strategies, which indicate that there are various techniques that can be implemented to track and manage the free blocks depending on the application's needs. Now, having covered all this, I believe that you have all the background that you need to proceed and do more tasks on the memory management concept. And in the end, thank you very much for listening, and we'll see you in the Q&A session.